Hola y bienvenidos. Ah, yo soy un profesor de estadísticas, profesor Garcha. Lo siento, lo siento. There we go. There. Okay, I think that's better. I think I had the Spanish on. Sorry. Alright, here we go. Alright, third lesson is on this LSRL idea, this least squares regression line. Now to start out, a little bit of review. Correlation, our R value, which I have right there. There's our R value. That is our correlation. Measures the strength and direction of a linear relationship. It must be linear. It will not measure any kind of curved relationship between two quantitative variables. We have to have numbers tied in. We cannot do any kind of categorical variables. Now, if our scatter plot shows a linear relationship, we would like to summarize the overall pattern by drawing a line through our scatter plot. This is the same idea I kind of talked about through the first lesson, where we're going to have this line. So now what we're going to talk about is, where's that line going to be? What's the equation of that line for our data? And we're more of an introductory lesson with this. And then we'll dive more and more into it. So today I'm going to show you two different ways to get the equation of this regression line. Okay. Definition of a regression line is a line that makes the sum of the squares of the vertical distances between the data points and the LSRL as small as possible. Now I'm going to draw in here what I really mean by that. And hopefully it will be very visual of how you will see the sum of these squares. So if this line right here was our least squares regression line, and they're talking about the vertical distances between the data points and the LSRL, which is your line, as small as possible, that's saying if I took this point here and drew a vertical line to it and made a square out of it and did all that with all of these points, that if you were to take all of these squares area and add them up, this would be the smallest possible sum that you could get. If you move the line in any way, the sum of these squares, the sum of all these areas of all these squares would increase. And then you wouldn't have the least squares. You would have the not least squares regression line. Now, you're not going to have to be able to do this by eye and go, well, I think this line works. You know, we don't have to calculate the area of all of these squares. The calculator is going to do that for us. It's going to know exactly where the least squares regression line is going to belong. Now, the purpose of a regression line is we're going to use it to make predictions, and that's what we're going to focus on today. And a requirement that we're going to need is we have to have explanatory and response variables already set up into our scatter plot. Alright, so here I've got a scatter plot representing father's height as our explanatory variable and mother's height as our response variable. So we want to see if you knew the father's height of a child, does that help predict maybe what the mother's height is? Do tall men always go after tall women? Do short men always go after short women? And vice versa. And you can kind of tell from this scatter plot that there maybe is some sort of positive association, but it's going to be a very weak. But you can see your points are pretty scattered about, almost in a circle. So the correlation value is going to be very, very small, very close to 0 in this case. All right. Now, if I said, could you draw a line that kind of fits the average of all of these points? If you sat there and tried to draw what you thought was the best line that went maybe halfway through all of these points, and what someone else would draw, and what someone else would draw, would probably be fairly different. Maybe some of them are close, but then you got to think about the slopes of the lines and where's the Y-intercept of the line really going to start at. So if I just threw this line out here, okay, that's the least squared regression line. Now, would that be the same line you would have drawn? Maybe, maybe not. Probably more on the not. Okay? But we're going to use this line, this least squares regression line, And again, that least squared regression line just means that if I were to take each point, go vertically to the line, either up or down depending where that point is, and we're to make a square from each one of those points. And you can see I could be doing this for a while here. Some squares are going to be bigger than others. Obviously, the farther away a point is from the line, the bigger the square is going to be. And I could come down here and do these as well. But I'm not going to do all these. That would just be ridiculous. But this is the line that produces the least amount of area for all of those squares put together. Okay? So what we're going to do is try to predict the height of Paul's mother, given that we know Paul's father is exactly 6 foot tall. Okay? So we know Paul's father's height, so we can come down here to this x-axis, find where Paul's dad is, which would be right here at 72 inches, and we would go up to our regression line, find where it hits it, and then shoot over to the y-axis, like so here. Except I don't really know why. Okay, interesting. Well, let me put a red vertical line here. You would go up there, and then over, and we would predict that Paul's mother, based on our regression line, would be about 64 inches tall. Now, is that true? Maybe, maybe not. In a case where the association is very weak, you have a lot more room for error in your prediction. If you had a very strong association, then you're probably going to be a lot more, your prediction is going to be a lot more accurate. Yeah, it still might be off by a little bit, but it's probably not going to deviate too much away. So again, the problem is, if I were to have you draw what you thought was the regression line, a lot of people might draw different lines, and based on your line, 72 inches may produce who knows what height for Paul's mother. Okay, so we're going to talk about 2 ways to come up with a regression line. Now, no line will pass through exactly all your points. That's a given here. You would have to have a crazy line that would go and hit all of these points, and then it wouldn't be a linear relationship at that point. Well, we want one that's going to fit as best as possible, that's going to produce the least squares, least sum of squares of all those squares that we could draw to our regression line. And that's why we're talking about, we want to predict y from our x. If we can use our horizontal axis to be able to predict our vertical axis values, then we want to minimize, or we want a line that is close as possible to the points in the vertical direction. And if you notice, that's why I was going up or down in the vertical direction to make those squares. And you might ask, well, why are we making squares? Well, for the same reason with standard deviation. If you took all of these deviations, and if you were to add them all together to kind of average them out, it would be 0. So we can't just take the average deviations from all of these points from our line. We have to square them to make some of the negatives positive, and then we add them all together, and so there's the sum of the squares. It's the same idea as the standard deviation that we talked about in chapter 1. Okay, so now back down here. In the example above, if we predicted Paul's mother's height to be 64 inches tall, and she turned out to be actually 67 inches tall, how much would our error would have been? Okay, we thought she was 64, she's really 67, we were 3 inches off. Okay, and this is going to be a topic we're going to talk about more eventually. Now, the one thing you will have to remember is which way to subtract this. And your error is going to be the actual value minus what you predicted that value to be. And one easy way people have remembered this in the past is that you are in AP statistics, so it is always the actual A minus the P predicted. Another word we're going to use later for error is called a residual. Residual and error are going to mean the same thing, but we're definitely going to use the term residual a lot more, especially in tomorrow's video. Okay, now if your actual value was less than the predicted value, you can have negative error or negative residuals. It just meant that you over-predicted instead of under-predicted. Alright, So again, here's this idea of the error, the residual here. And here's where I'm actually going to talk about it. So what we want to do is this line, we want to minimize these distances as much as possible, so that when we make those squares, because again, all of these residuals, if you were to add them together, here you're going to have a positive residual, here you have two negative residuals, that they would cancel each other out in the end if you took all of your data points. Okay? So the formula is, again, actual minus predicted. Just remember AP, you're in AP statistics. Now here's what might get a little confusing. We're going to have two different kinds of y's. We're going to have a regular y, which represents your actual y value. And then we're going to have our predicted value that we're going to get from our regression line. Now this is pronounced y hat. And it's just a y, and you put a little hat on top of it. Put a little rooftop on it. But the predicted value is always going to be y hat. And when we write the equation of a regression line, or least squares regression line, it's always going to be y hat equals, and then the equation of that line. So we'll do more examples of that where you'll see, you're always going to have to write y hat for those regression lines. And if you leave it out, then you're not actually using a prediction line, you're using an actual line. So the LSRL of your y variable, of your response variable, using your explanatory variable, is the line that makes the sum of the squares of the residuals as small as possible. Okay, there will be some point where the line, the sum of the squares, unless your points make a straight line, then the sum of the squares will be 0, because there would be no error for every point if it is exactly on the line. Now, if your points are deviating a little bit, then there's going to be some error you can't get rid of. Okay, and you can minimize it as much as possible, that it's as close to 0 as you can get it. All right. Now, here's a feature that we're going to use here in a bit towards the end of the notes. But every regression line will always pass through the point, the mean of the x and the mean of the y. This is something we're going to use later on with some calculations. So keep this in mind. This will be an important part, that every regression line will pass through the mean of the x, comma, the mean of the y.
Lastly, let's look at the actual equation for an LSRL. So if you guys remember y equals mx plus b from your Algebra 1 days, we're going to use a variation of y equals mx plus b. But what we do in stats is, for whatever reason, it's kind of unbeknownst to me, but they kind of flip the mx and the b part. And we don't really use m and b anymore. We still use b, but it takes on a different meaning in this case. But in stats, we're going to use y hat equals a plus bx. Okay, this is b times x here. It's not just one variable bx, but b times x. The y hat here is our predicted y value that we're going to hopefully be able to predict, and we might be off, we might be on, we never know. And the x that we're going to use is going to be the actual x value from our data that we can try to use there. Now the a in this case is our y-intercept. Before, with y equals mx plus b, the b was our y-intercept. Now it's the a. It's still the thing that's not attached to the x like it was in y equals mx plus b, right? The b was the thing that's kind of solo by itself. The a is the thing that's kind of solo by itself. So it still applies, just a different letter. Now, if you remember how to interpret the y-intercept, that was the point on the graph where the line, or really any graph, it didn't have to be a line necessarily, but when we did y equals mx plus b, we were doing lines. But the y-intercept for lines was when the line crossed through the y-axis. And if a line crosses through the y-axis, that means that the x value had to be 0. So to interpret the y-intercept, just in general, kind of a generic interpretation, would be when x is 0, then our predicted y will be whatever that a value was there. Okay? And for the slope, which is now our b value, which is still the same thing that's attached with x like it was in y equals mx, it's now bx. So its interpretation, if you remember slope, it was rise over run, right? So we would subtract our y's, be y minus y over x minus x. So we're talking about a change in y over a change in x. So the interpretation part starts with the x part, though. So it kind of starts with the denominator. So we're going to say for every one, whatever x is, increase, and it's always going to be an increase, but for every one increase in x, whatever x may be, we predict an increase or a decrease. And you might go, well, how do I know if it's an increase or a decrease? Well, it all depends on the value of the slope. So it's an increase if b is positive, or it's a decrease if b is negative. Okay, so you got to make that decision there. If it's positive, increase. If it's negative, decrease of our whatever our b value is in y, because we're trying to predict y. So let's put this to use to finish out the video. So let's say our mother-father height scatter plot from earlier, let's say this is the regression line. Okay, and I just kind of made this up based on what I felt like would be maybe the LSRL. But in the next video, we'll talk about how to get this equation. So don't fret about that. You'll just be given this for right now. It says determine and interpret the slope and the y-intercept values. So first, if I were to determine the slope, well, the slope's the value that's with our x. So it is the 0.962. Now, to interpret what that meant, I need to know what was x and what was y. And we were trying to predict the mother's height. So what we were trying to predict is y, and what we were actually using, which was the father's height, that is x. All right, so I'm going to say for every, and then I had to say for every 1x, right? For every increase in 1x, where x is the father's height, but what is the height units in? And it was in inches. So we're going to say for every inch, we could say for every inch, that implies 1, right? We can get away with that. Or we could just say for every 1 inch of additional height, for the father, we predict an increase, because our slope was positive, an increase of 0.962 inches in the mother's height. Okay, so technically the mother is shorter than the father on average. So for every 1 inch you would have of your father's height, you could take 0.962 inches of that 1 inch and apply it to your mother's height. Okay, there are some little words that you could, do without, or, but basically it has to be for every 1x, for every 1 inch in dad's height and father's height, we predict the mother's height to increase by approximately 0.962. So there I just said that a different way than what I wrote it. Okay, you can mix around the order of this second part of this statement. Again, I said we predict the mother's height to increase by approximately 0.962 inches. Okay, so again, there's a different way you can rearrange the order of some of this stuff. All right, the y-intercept, well, that's the 57.3. So how do we interpret this? Well, earlier we said when x is 0, then our predicted y will be the a value. Okay, so what this means is when the father is 0 inches tall, we predict the mother to be 57.3 inches. Now, does that make sense when dad is basically non-existent? We have mom that's 57.3 inches. Does that mean mom, I don't know, did like in vitro fertilization and didn't really need a dad, or what's going on here? What you'll find a lot of the times with the y-intercept interpretation is that it's not really going to make sense, but we still can interpret what that really means. Just in actual context, it may not make much sense. All right, so that is all for this video. And again, in the next video, we'll talk about how do we actually get this equation. We'll talk about how to get it with the calculator and how to calculate it by hand when given certain information.